illustrate a few problems on computation of magnetic fields for some simple geometry and combination of those. Now, the first one that we have is a very long, straight long wire. We have a very long wire carrying a current I. And it's bent in the form of an L. This is the L that you see. This is a very long current carrying wire bent in the form of an L. It's bent at the point O. It's bent at the point O. Now, if you call it the x-axis, you call it the y-axis, then in this plane there is a point A comma A. We want to be able to now compute the magnetic field for this. Now, all that you need to do here is, you need to look at two wires separately. One along the y-axis, coming from infinity all the way to the point O, which we can refer to as the origin, and then from O all the way to infinity, right? So, realize that if this is the point A comma A, right, then evidently this is A units, this is A units, evidently this will be theta 2 equal to 45 degrees, and if you think about it, this is A and this is A, this will also be theta 1 equal to 45 degrees, right? Now, to compute the magnetic field due to 1, see, at a distance r, this is at a distance A. This wire is at a distance A from this point. So the magnetic field at P, because of this, is going to be mu naught I divided by 2 pi A, right, into cos theta 1 plus cos of this other angle. You know, the other angle would be the point there is going to be at infinity, and the other angle theta here is going to be 0. So cos 0 divided by 2. That's the magnitude of the field because of this. And the direction, realize that if dl is like this, r is like this, dl cross r would come out of the plane of the board. So because of this, the field at P would come out of the plane of the board, right, which is in the plus k direction, k cap, plus the field because of this. The field because of this is going to be mu naught I divided by 2 pi, this distance, perpendicular distance, this realizes A, this is A, 2 pi A, cos theta 2, theta 2 is 45 degrees, cos theta 2 plus the other angle which would be at infinity would be 0, right? So cos 0 divided by 2, and the direction, okay, if dl's are like this, if r is like this, if dl's are like this, r is like this, because of our dl cross r, this also comes out of the plane of the board. dl cross r would come out of the plane of the board, right? So in this case, the field would be in the plus z direction, so k cap. That's going to be the field. So this will then become mu naught I divided by 4 pi A, cos 0 is 1, cos 0 is 1, 1 plus 1, 2, plus cos theta 1 plus cos theta 2 is 2 cos theta 1, means 2 cos 45 degrees, right, k cap, which could then be written as, so that's a magnetic field at the point P vectorially, which is like mu naught I divided by 2 pi A into 1 plus 1 by root 2 k cap. That's the magnitude of that's the field at the point P, magnetic induction at the point P for this L-shaped structure. Thank you so much. Bye. So here we have 4 wires. This is 1, 2, 3 and 4, right? This is very long, right? And there is a current I that is being carried. I want to be able to compute the total magnetic field, magnetic induction at the point O as shown. Given that this point is A00, 0, this point is 0, 0, A, and very clearly, you know, as far as the point B is concerned, its x coordinate would be A, its y coordinate would be 0, and its z coordinate would be A. That's what it is, right? So I want to compute the total magnetic field at O because of this arrangement. Now look at wire 1. That suppose produces magnetic field B1 at O. See, if a wire if a very long wire passes through a certain point, then it produces no field about that point. So the field produced at O because of 1 is going to be 0. If there is a wire and I select a point A on the wire, then the magnetic field at A produced is going to be 0. Right? So B1 is 0, magnetic field produced by 1 at O is going to be 0. Now, by 2, let's say 2 produces magnetic field B2 at O. This is the wire 2. Now, would you want to believe that this is a right angle triangle, this is 90 degrees, right? And evidently this length is A units, this length is also A units. That means, you know, it's an isosceles right angle triangle. This is 45 degrees, this is also 45 degrees. So now, the field produced at O because of this finite wire carrying current I, finite wire carrying current I is going to be mu naught I divided by 2 pi. Now, what's the distance of 2 from O? This is the, what is the distance of the wire 2 from O? Can you see that? It is this. This is the distance, which is A units, 2 pi A, right? Distance of this wire from O, see this is 90 degrees. So this is 2 pi A into cos, cos 90 plus cos 45 by 2 using the formula cos 90 plus cos 45 divided by 2. Cos 90 plus cos 45 divided by 2. What's the direction of B2? See, DL is like this, R is like this. Would you not want to believe that this wire produces magnetic field in the Y direction? See, I hope all of you are at home. Suppose this is my x-axis, this is my z direction, this is my z direction. In the xz plane there is a wire, in the xz plane there is a wire carrying a current I. So my DLs are like this and my Rs are like this. Rs are like this for different DLs. These are my Rs. This is the wire. So would you not want to believe that DL cross R comes out of the plane of the board, which is the Y direction, DL cross R. So B2, because of this, is in the Y direction. So into, let me write into K cap, right? So I've run out of space here, so I write it here. B2 is this, right? What about B3? Okay. So again, realize that this length is A units, this is also A units, this is evidently 90 degrees. So this is 45 degrees, this is also 45 degrees. Now, the field produced at O because of 3, B3 is going to be what's the distance of this wire from O? A units. So mu naught I divided by 2 pi A. Now, cos 45 plus cos 90 by 2. By 2. And then direction. DL is like this. R is like this. So, what are my DL cross Rs? What is my DL cross R? DL like this. R like this. Do you want to believe that DL cross R would come out of the plane of the board? DL cross R, see, this is a wire in the XZ plane, this is a wire, so let me call this is the XZ plane. So I'm drawing the XZ plane like this, and Y comes out. So this is this wire parallel to the Z axis, DL. So my DLs are like this, this is the origin, DL cross R. So DL cross R comes out of the plane of the board, that means in the Y direction. See, DL cross R gives me the direction of the magnetic field. Biot DL cross R comes out of the plane of the board, right? So, K direction, J direction, actually, this should also have been J direction. This should have been J direction. All in the Y direction, this was also in the Y direction. So, J cap, right? What about, so that's B3. What about B4? B4 again is going to be mu naught I divided by 2 pi A. Again, notice that this is cos 90 this will turn out to be 0. Very large distance, this will be 0. So that's going to be cos 90 plus cos 0 divided by 2. Cos 90 plus cos 0, cos 90 plus cos 0 divided by 2, magnetic field produced by this. And direction, these are my dls. This is, for example, the r. So dl cross r comes out of the plane of the board in this case. If this is the xy plane, then dl cross r comes out of the plane, which is the z direction. So k cap. All that you need to do is, the net magnetic field at O is going to be the vector sum of B1 plus B2 plus B3 plus B4. That's going to be the net magnetic field at O. Yes or no? Right? Thanks a lot. So here's another problem. We have two very long wires, 1 and 2, thin long wires, 1 and 2, and the current coming out of the plane of the board. And there is a point P in the plane of the board at a distance h symmetrically located with respect to 1 and 2. We want to be able to compute the field at P. Now, what we'll do is, we'll compute the field at P because of 1 and because of 2, and then we'll add. Say because of 1 alone, this was wire 1, right? Realize that the field at P because of 1, this is P because of 1 will be, so what we'll do is, since the current is coming out of the plane of the board, we curl the fingers like this, right? The thumb coming out of the plane of the board. Do you see that the curling takes place like this? That means now, in order to compute the field at P, what we'll do is, we'll draw a circle around this current carrying wire, circle of radius r around the current carrying wire, and the field will be in this sense, curling of the fingers. That means the field will be perpendicular to the wire, obviously, as we know, and will be like this, That will be the field at P because of 1. And suppose this angle is theta. Would you not want to believe that this is theta, this would be theta? So this will be theta. So B could have been resolved as B cos theta upwards and B sin theta horizontal. B cos theta upwards and B sin theta horizontal. Right? That's the field at P because of 1. B cos theta upwards and B sin theta leftwards. Now, see, again, I want you to be very clear about this. To compute the field because of a current carrying wire, put your thumb in the direction of the current, curl your fingers. That means now you circle this. The circle will go this way, will be traversed this way. At a distance r, the field is going to be, in this sense, tangential to the circle at P. Right? And B, magnitude of B very clearly is going to be mu naught I divided by 2 pi small r, which could be resolved as B cos theta upwards and B sin theta leftwards. That's because of 1. What about 2? Let me look at 2. Let me draw it right here again. Because of 2, this length will still be r, right? And I draw a circle like this. And this time, the curling of this circle also takes place in this sense. Thumb pointing out, and then the field is going to be dl cross r, this way. That's going to be the field at P because of this. So that's again going to be B, same magnitude, mu naught I by 2 pi r, right? Which could again be resolved as, say, this B will make an angle theta with the vertical, right? B again, this B because of 2 could be resolved as B cos theta downwards and B sin theta leftwards, right? And would you not want to believe that this B cos theta will get cancelled with this B cos theta? All that we are left with is 2B sin theta. So the net field is like leftwards and is of magnitude 2B sin theta. 2B sin theta means 2 into B. B is mu naught I by 2 pi r. I divided by 2 pi r. What is r? R is root h square plus a square into sin theta. What's theta? Theta is this. So this is y, this is a. Sin theta is very clearly y by r. y by r or h, say h by r, h by r, h by r, h by r, r again could be, so this is like, this will get cancelled, mu naught I divided by pi, r is also root h square plus a square, so this will become h square plus a square into h. That's the magnetic field at a distance h from the midpoint of the line joining these two very long wires. Yes or no? Right? So what we have in this situation is two infinite sheets of current, thin infinite sheets of current carrying current perpendicular to the plane of the board with linear current density J, linear current density J. And there are three regions, A, region B, and region C. We want to be able to compute the magnetic field at points in region A, at points in region B, at points in region C. Now, let me look at region A. First of all, realize that the magnitude of the magnetic fields, because of any one of these two, because the linear charge density is J, so the magnitude of the fields is going to be B1 equal to B2 equal to mu naught J by 2, mu naught J by 2, right? That's a standard result. I'm assuming you know this result. Now at the point A, because of this, B1 would be leftwards and B2 would be rightwards. B2 is because of 2. This is current going into the plane of the board. So right above this, see, all these B's will be parallel to the infinite sheets of charge. All the B's would be parallel to the infinite sheets of charge. So then, because of this, what we do is we take the current coming out of the plane of the board using this thumb. And notice this, the way we'll circle this is like this. So the B would be in this sense. B would be parallel to B1 would be like this. For this, think of it like this. Thumb going into the plane of the board, curling this way. B2 would be this way. B2 would be this way above this. And if B1 in region A is like this, in region B, B1 would be like this. For 2, above this, B2 is to the right, but below this, B2 would be to the left, right? What would then be the net magnetic field in regions A, B, and C? In region A, B1 and B2 will get cancelled, so B would be 0 in region A. What about region B? B is going to be twice B1. Twice B1 is mu naught J and would be to the right. And in region C, B1 and B2 would again get cancelled and the magnetic field will be 0 here. Yes or no? Which means what we have is between these two infinite sheets of current, we have a region of uniform magnetic field in this and 0 here and 0 here. So this is a region of uniform magnetic field depicted with by magnetic field lines this way. This would be a region of uniform magnetic field mu naught J and 0 magnetic field above and below this. Yes or no? Thank you so much. Bye. That involves computation of magnetic field, magnetic induction. We have a strip of width L and of infinite length digging into this plane, carrying a current of linear current density J, current per unit width is J. We want to be able to compute for this geometry the field at a point P on the y-axis, y from the origin, y units from the origin. What we need to do is, we need to break it up into several thin wires, infinitely long, plunging into the plane of the board and compute the field at the point P for each one of them and then perform a summation, either a scalar summation or a vector summation. Let's look at what to do. So what I do right away is I select a small portion at a distance x. I select a thin wire of thickness dxa. This is almost like a thin wire and I have a result known to me for a very thin wire, field at a distance r from a thin wire. So suppose this dx is at a distance r. This dx is at a distance r from this and say this angle is theta. I'll compute the field because of this dx at P. Now again you can see the field because of this would be dB like this, perpendicular to r. I hope you realize the direction. take your right hand and plunge. See, this is current density, current going into the plane of the board. So we take our right hand and point our thumb into the plane of the board. The fingers curl in this sense. That means dB must be like this. dB must be like this. All that you need to do is you need to look at a circle like this, centered at this, and then the field will be along the tangent. It could either be in this direction or in this direction. The way to find this direction is either do a dl cross r. Dl cross r realizes dl is like this, r is like this, and dl cross r would be this. Or what you can do is right hand, thumb into the plane of the board, and look at the curling. The curling is in this sense, so dB would be like this, perpendicular. See, it could either have been like this or like this, but because of the right hand rule, it goes this way, this way. So then, in any case, that's dB for this. And the value of the magnitude of dB is going to be mu naught times I associated with this is going to be j into dx. J into dx, j is the linear, divided by 2 pi r. That's the dB for this, right? And if this is theta, realize that this is also theta, and this is p, this is also theta. dB could be resolved vertically as dB cos theta and horizontally as dB sin theta. We'll add up the dB cos thetas by allowing x to go from 0 to L. We'll add up all the dB sin thetas, allowing x to go from 0 to L. So the net field in the y direction would be sum of all the dB cos thetas, sum of all the dB cos thetas, where dB is like mu naught j dx divided by 2 pi r, and cos theta, what's cos theta? Cos theta is x by r, so x divided by r, this will become r squared, right? Where x runs from 0 to L, x runs from 0 to L. So this is like mu naught j by, mu naught j can come out by 2 pi integral x divided by r squared. R squared is like a y squared plus x squared dx. X runs from 0 to L. This is the integral. Now I'm integrating with respect to x. Numerator can be made the derivative of the denominator by multiplying by 2, dividing by 2. So that's like a mu naught j by 4 pi log of the denominator, which is like log of y squared plus x squared. X changes from 0 to L, which is like mu naught j by 4 pi, mu naught j by 4 pi log, when x is 0, when x is L, it's like y squared plus L squared. When x is 0, it's like a y squared. That's the net field in the y direction. What's the net field in the x direction? Sum of all the dB sin thetas. So the net field in the x direction is sum of all the dB sin thetas, where x runs from 0 to L. Let's integrate this. I can write dB as mu naught j dx by 2 pi r. 2 pi r. Sin theta can be written as y by r. R, so this will become r squared, and x runs from 0 all the way to L, right? X runs from 0 all the way to L. So this is like mu naught j y divided by r squared. R squared is x squared plus y squared dx. X runs from 0 to L. Let's integrate this. So this is like mu naught j y taken common, and then 1 by y tan inverse x by y. X by y, x runs from 0 to L. So how much does this turn out to be? This turns out to be mu naught j. Of course, there is a 2 pi which I missed out. There is a 2 pi that I just happened to miss out by 2 pi. And then 1 by y tan inverse 1 by y tan inverse x by y. So this is mu naught j by 2 pi tan inverse L minus tan inverse 0. That's the field in the x direction. And the net field, therefore, vectorially, because of this, at the point P is going to be this bx, which we have computed, bx I cap plus by j cap. That's the net field. Yes or no, right? Thank you so much. Bye. So this one situation, which is about a hemisphere of radius r, and there are n turns of a closely wound wire, each turn carrying current I, and because of this arrangement we want to be able to compute the magnetic field at O. What we do is we break this entire surface into several circular rings, starting from so this is a sample ring that I have selected at an angle theta as shown, right? This is the location of the ring. This is theta, and the width of the ring is given by d theta, so this is going to be r d theta, the width of the ring. And the radius of this ring is r sine theta. We will compute the field at O because of this ring, and then do a summation. The field at O is going to be along the axis. While we do the summation to cover all the rings, starting from here all the way to the equator, we take would be about theta equal to 0, and the topmost ring would be about theta equal to pi by 2. Now there are n turns of the ring, right? There are n turns of the ring, and realize that this is the first turn, second turn, third turn, fourth turn, nth turn. So number of turns per unit length along the circumference, is going to be n by pi r by 2. So now the field at O because of this chosen strip is going to be mu naught I times number of turns contained here. How many turns are contained over r d theta? Number of turns contained per unit length is n by pi r by 2. How many turns are contained over r d theta? These many turns. Into square of the radius, which is r sine theta whole square, divided by r cubed, this cubed, with a 2 here. That's the field at O because of this, and it's going to be along the axis. Each of the rings starting from theta equal to 0 to theta equal to pi by 2 would make a contribution along the axis, and therefore all that I need to do is carry out a summation where theta runs from 0 all the way to pi by 2. How much is it? So see, r squared, r cubed will get cancelled. We then have like a mu naught ni divided by pi r. This 2 will get cancelled with this 2, and then we have integral sine square theta d theta. Theta runs from 0 to pi by 2. I could have rewritten this as sine square theta as half of 1 minus cos 2 theta. Theta runs from 0 to pi by 2. This is mu naught ni divided by pi r. Sine square theta is half of 1 minus cos 2 theta, right? D theta. And very easy to see, this will be 0 on integrating from 0 to pi by 2. What we are simply left with is mu naught ni by 2 pi by 2 pi by 4. So pi by 4 pi r, 4 pi will get cancelled. So that's simply mu naught ni by 4r. That's the field at O because of this entire arrangement. Yes or no? Thank you so much. Bye. So this time there are two loops. One of radius b, which say lies in the plane of the board, right? And its axis is like this, coming out of the plane of the board. And there is another loop like this, whose axis is perpendicular to the axis of this loop, right? That means say the axis of this could lie in the plane of the board. So these are two perpendicular circular loops of radii a and b. This one carries current I1, this one carries current I2, and we need to be able to compute the field at C. So now for this, what's going to be the field at C because of this? Mu naught I2 divided by 2 pi b. And what's the direction? See, this is my x direction, this is my y direction. What comes out of the plane of the board is the z direction. So in this case, curl your fingers in the sense of the current. The thumb points out. So that's the z direction. So k cap. That's the field because of this coming out of the plane of the board. What about this? The field is going to be of magnitude mu naught I1 divided by 2 pi a. Mu naught I1 divided by 2 pi a. And what's the direction of the field? This is the magnitude of the field created by this at C. What's the direction of the field? Alright, curl your fingers like this, because if you see this way, if you see like this, then the current is going this way. And if you curl your fingers in the sense of the current, your thumb points in this direction, which is the negative x direction. So minus I cap. Minus I cap. That's the field at C. That's the field at C. Yes or no? Thank you so much. So in this problem we have a very long cylindrical wire, very long cylindrical wire, carrying a total current I naught. I naught is the total current flowing through this cross section. This is the cross section of the very long cylinder wire of radius r. And there is current density. In this case, current density is current per unit area. Current per unit area is given as a function of small r, distance from the center. Distance from the center, the current density is given by J naught, small r by capital R. We want to be able to compute the magnetic field inside and outside as a function of small r, distance from the center of O of this cylinder. So what do we do? Okay, what we can do is, let's say for small r less than or equal to capital R, we look at an Amperian loop like this. We look at an Amperian loop like this, right? And then the B at every point of this Amperian loop from symmetry considerations will be along the tangent and would be of the same magnitude, So the line integral along this is going to be B into 2 pi r, and that must be equal to mu naught times the total I enclosed up to r, up to small r, right? Now that means I need to compute the total current flowing through this cross section. What I do is, in this cross section, within this cross section, suppose I had to look at a radius small r, or let me call it small x, a radius small x, within the small r and of thickness dx, right? Then the current flowing through this is going to be what? 2 pi x is the circumference into dx is the thickness. That's the area of the shaded portion, into the current flowing through this is going to be J naught, right? The current flowing through this is going to be current density associated with x, J naught, x by capital R, right? The total current flowing when x runs from 0 to small r would be sum of all of this. X runs from 0 to small r. That's going to be the total current flowing through this cross-sectional area. So how much does this turn out to be? This turns out to be 2 pi J naught by r, 2 pi J naught by r, 2 pi J naught by r. X square, when I integrate, I get x cube by 3. So r cube by 3. That's the total current. Up to small r, right? So this is going to be mu naught times I enclosed up to small r, I in this region, which is 2 pi J naught by 3r into r cubed, right? That's B into 2 pi r from Ampere's circuit law. ACL is Ampere's circuit law, and this is my Amperian loop. And I have applied Ampere's rule to this loop. Line integral B into 2 pi r must be mu naught times I enclosed up to this. So then again, easy to see, this r and this will become r squared and then we have 2 pi getting cancelled with 2 pi, and then we have B equal to mu naught J naught divided by 3r into small r squared, right? That means within the cylinder, B as a function of distance from the center is going like this. What about outside the cylinder? For points outside the cylinder, what we need to do is for this was my cylinder of radius capital R, and for points outside the cylinder, this is small r greater than or equal to capital R. Again, I do a B dot dl. This is the cylinder, capital R, right? And this is small r greater than capital R. This is a point P chosen outside the cylinder. B like this, B going this way, and I do a line integral of this. So for r greater than or equal to capital R, B into 2 pi small r equal to mu naught times the total current I naught enclosed inside this. So then B then turns out to be mu naught I naught divided by 2 pi r for r greater than capital R. Yes or no? So this is R greater than capital R, or greater than or equal to capital R. It does not matter. It will be a continuous function. So then inside the cylinder it goes as R squared, a parabola. Outside the cylinder it's hyperbolic. It decreases as 1 by R. So then the variation of B versus R is going to be at small r equal to 0, it's 0. Then it increases like a parabola, B increases like a parabola, and then on the surface there is a transition, that is small r equal to capital R, and it decreases like a rectangular hyperbola. This is what happens, right? That's the variation of B versus R. Obviously, as R tends to infinity, B will tend to 0. B into small r is a constant, so B versus small r for this region is going to be a rectangular hyperbola. That's how it goes. I hope all of you understand everything here. Thanks, bye. Now here we have a very long cylindrical conductor, and let's say it's throwing up current along its axis in this direction, longitudinally, a current density J, a uniform current density J. Now what's done is, in this very conductor with uniform current density, this is current per unit area, by the way, right? Current density J, current in this direction, and a long cylindrical cavity whose center is different from O is produced. This is a long cylindrical cavity. We want to be able to find the field inside this cavity. Now very clearly, you know, if this cavity was not there, and say I look at a point P whose position vector is R1 with respect to O, then the field at P, as you know, is like a mu naught by 2 J cross R1 would have been the field at P, right? But now when this cavity is created, I will have to remove the contribution made by this cylinder. Suppose this vector is R2, this vector is R2, then the contribution made by this would have to be removed once I create the cavity. So that's going to be minus mu naught by 2 J cross R2, J cross R2. So that's the field at P, that's the field at P. So that's like a mu naught by 2 J cross R1 minus R2, J cross R1, assuming J is out of the plane of the board for convenience, J cross R1 minus R2, and realize if this is R1, then this is minus R2, and then O to C is a constant vector. R2 is a variable vector because P could be anywhere inside the cavity. R1 is a variable vector because P could be anywhere inside the cavity, but the cavity is fixed. So the center of the cavity and the center of the original cylinder, they are fixed. So the vector OC is fixed. So R1 minus R2 is the vector OC, which is R, So mu naught by 2 J cross R, J cross R. Hey, J is a constant, R is a constant, so J cross R is a constant. J cross R is a constant. That means the field anywhere inside this cavity is a constant and is mu naught by 2 J cross R, right? Which means now inside the cavity, if this was the cavity, and say if J was coming out of the plane of the board, if J was coming out of the plane of the board, then J cross R would be like this. J cross R would be like this. This is the center C. J cross R, you might want to check, will be like this. So the field inside the cavity, if the current is coming out of the plane of the board, is going to be uniform and directed this way, and would be represented like this, very clearly. And the magnitude of BP is going to be mu naught J into R, because J and R are perpendicular. Yes or no? So here we have a very long cylindrical wire of radius capital R, and there is current density J, which is not constant. The current density, current per unit area flowing through this is not a constant, is a function of the radial distance from O. That's given. And consequently, it is found that the magnetic field inside the cylinder at a distance small r from the center is given by C r to power alpha, where C and alpha are constants. We want to find how J varies with R inside the cylinder. That's what we want to be able to find, right? Good. All that we need to do is we need to select an Amperian loop of radius small r centered at O and apply Ampere's circuital law to this, right? So evidently, if I take the line integral of B, then B into 2 pi r, and that must be equal to the total current enclosed, mu naught times the total current enclosed, J at r into 2 pi r dr, where r runs from 0 to small r. That's the total current. This is current per unit area for a strip 2 pi r, radius r, thickness dr, that's the area. And then small r varies from 0 to small r. That will give me the current enclosed inside this region. So that's Ampere's circuit law applied to this region. I want to find J as a function of r, right? So first of all, let me remove the clutter from here. 2 pi gets cancelled. And B is written as C r to power alpha. So this becomes C r to power alpha plus 1 is mu naught times 0 to small r J at r into small r dr, right? I'll apply Leibniz rule of differentiation under the integral sign to scoop JR out. So when I do that, then I end up getting C alpha plus 1 into r to power alpha equal to mu naught J at r into r. When I differentiate both sides, right, the integral vanishes. And then we get J at r is C by mu naught into alpha plus 1 into r to power alpha minus 1. That's what we get. That's what we get. J as a function of small r. Right? So this again is an interesting simple problem, but application of Ampere's circuit law. Thank you so much. Bye. So in the next problem, what we have is a cone, and there is a wire of n turns wound around the cone uniformly. So the windings range from let's say L1, they start from L1 and they go all the way to L2 along the slant length of the cone, right? The semi-vertical angle of the cone is, say, theta. I is the current per unit turn and N are the number of turns. We want to be able to compute the magnetic field at P because of this. So what we do is, again, logically, we break it up into circular strips of this kind, circular rings of this kind. And for each of these circular rings, for example, this is a circular ring selected at x along the slant height and of radius very clearly x sine theta. If this is theta, this radius is x sine theta. And we'll compute the magnetic field at P because of this chosen ring selected along the slant height at a distance x along the slant height and of radius x sine theta. This is the ring. This is the ring. Now, very clearly, you know, it's going into this and it's coming out of this. So it's like this. Like this. So the field at P because of this is going to be dB like this. Is going to be dB like this. Field because of each of these rings starting from x equal to L1 going all the way to x equal to L2 would be axial, and we need to sum up our limits of integration would be x ranging from L1 to L2. So let's compute the field because of this chosen strip at the point P. What's that field going to be? The field is going to be dB equal to mu naught number of turns over dx. Hey, the number of turns over L2 minus L1. This length is L2 minus L1 because this whole thing is L2 and this is L1. So this length is L2 minus L1. So the number of turns per unit length along the slant height is n by L2 minus L1. So over dx, the number of turns is going to be this into the current I per unit turn divided by 2 into square of the radius, which is x sine theta whole squared divided by r cube, which is x cubed, right? Where x runs from L1 to L2. X runs from L1 to L2. I need to sum it up. That's the net magnetic field and it's going to be axial. Let's see what it turns out to be. This is like mu naught Ni by twice L2 minus L1. And then we have x square sine square theta also coming out, and then we have like a 1 by x to be integrated. So log x, 1 by x, log x, so log 2 by log 1. Log 2 minus log 1, which is log of L2 by L1. That's the magnetic field produced at the point P with an ordinary integration with this kind of a selection of strips. Yes or no? Thanks. So what we have here is a semicircular wire QS carrying a current I centered at O. and we complete the circle, and this is one end of the diameter P. We want to be able to compute for this current carrying wire the magnetic field at P, right? So in all our previous digressions, we've looked at magnetic field at the center of a circular loop or an arc, etc. But this time, we have a different kind of a point P, where we want to be able to compute the magnetic field. So again, not difficult, just a little different. What we do is we select from the vertical an element at an angle theta. That element is, say, subtends an angle d theta at the center. This is our element rd theta. This is our element rd theta, the dl in Biot-Savart, that is carrying current. And for this rd theta, we want to compute the magnetic field at P. And then we'll sum it up. We'll cause theta to vary from minus pi by 2 to plus pi by 2, covering all elements on this semicircular wire. Also notice that the field at P, because of this, see, dl is like this, r is like this, dl cross r goes into the plane of the board. This is my dl. See, the dl cross r, dl is the current carrying element, r is the position vector of the point P from the current carrying element, and in this case, see, dl cross r goes into the plane of the board, and therefore the field, because each of these elements would be into the plane of the board, so then we don't have the headache of dealing with directions of the magnetic field. Magnetic fields produced by all elements here would be in the same direction, and therefore we have to sum them up like we add scalars. So then what I do is, in the first place, I'll compute the magnetic field because of this dl, which is rd theta, at the point P, and then sum it up by changing theta from minus pi by 2 to plus pi by 2. Now let me do my angle selections. This is theta. So now this is radius, this is also radius. An exterior angle is sum of two interior opposite angles. Therefore, this is theta by 2, this is theta by 2. And r is the distance of this element, distance of this chosen element, let me call it element chosen at T, from the point P where we want to compute the magnetic field. Now, very clearly, the magnetic field at P, because of this rd theta, would be of magnitude given by dB is mu naught by 4 pi I dl. dl is rd theta cross r. Cross r means into r into sine phi into small r into sine phi divided by r cubed. Right? That's Biot-Savart law, and it's going into the plane of the board. Now, we have mixture of things between theta and phi. Let me write everything in terms of theta. I'll make theta the subject of my integration. So first things first, look at this triangle. OTP, we have r squared is capital R squared plus r squared, that is 2r squared minus 2r squared into cos of this angle. Cos of this angle is what? Cos of pi minus theta. Realize that if this is theta, this angle is going to be pi minus theta, right? This angle is going to be pi minus theta. So which is like 2r squared into 1 minus cos pi minus theta is like a 1 plus cos theta, right? So this is like 2r squared, 1 plus cos theta is 2 cos square theta by 2. So very clearly small r is 2r cos theta by 2. Small r we know in terms of theta. So this small r we know in terms of theta. What about phi in terms of theta? Realize that phi plus theta by 2 is 90 degrees. This is phi plus theta by 2 is 90 degrees. Phi therefore is 90 minus theta by 2. Right? So let me write everything in terms of phi. Now this will then become mu naught I by 4 pi r by r squared, r by r squared, sine phi is sine 90 minus theta by 2, sine 90 minus theta by 2, so that makes it cos theta by 2, right, into d theta. Yes or no? I hope all of you understand this. Mu naught I by 4 pi, this becomes r squared, that capital R features here, sine phi becomes cos theta by 2, sine phi is cos theta by 2, d theta, and so on and so forth. And this small r squared in the sitting in the denominator is like a 4r squared cos square theta by 2, cos square theta by 2. So this goes away, this goes away. That's dB because of this chosen element. The total magnetic field will be sum of all of this, where theta varies from minus pi by 2 to plus pi by 2. That's the magnetic field. That's the net magnetic field, which is like a mu naught I divided by 16 pi r, right? 16 pi r, and then this is integral sec theta by 2 d theta 0 to, sorry, minus pi by 2 to pi by 2. Now, sec theta by 2 is an even function. So what we can do is, if it's an even function, minus a to plus a would be twice 0 to a. So into 2, and I can change this to 0 to pi by 2. 0 to pi by 2, right? And then I can make theta by 2 my subject of integration. So I can write this as theta by 2. And then multiplying by 2. So that makes it another 4. Right, I hope. And theta by 2 varies from 0 to pi by 4. Theta by 2 varies from 0 to pi by 4. So then this is like mu naught I divided by 4 pi r. Mu naught I divided by 4 pi r integral sec t dt, where t runs from, t is theta by 2, t runs from 0 to pi by 4. And what does it turn out to be? This turns out to be mu naught I by 4 pi r log mod sec t plus tan t, t runs from 0 to pi by 4, right? Which is like mu naught I by 4 pi r. At t equal to pi by 4, this will become 1 by root 2 and this will become 1, right? So log 1 by root 2 plus 1 divided by, at t equal to 0, sec 0 1, and this will be 0, right? Sec 0 is 1 and tan 0 is 0. So 1, this is what becomes of it. Sorry, so at t equal to 0, at t equal to pi by 4, it'll become 1 by, it'll become root 2, beg your pardon. Sec pi by 4 is root 2 plus 1, and then at t equal to 0, it'll be 1 plus 0, right? So this is what becomes of it. So this is like a mu naught I by 4 pi r log 1 plus root 2. That's the magnetic field at the point P and going into the plane of the board. Yes or no? So again, a little bit of a different problem, but it helps us get a feel for how to do computations related to the magnetic fields. Thank you so much. Bye.